Hello, future physicists. Welcome back to Dr. Liu's VCE Physics channel. Today, we are diving into the 2024 NHT Physics exam, specifically tackling the Newtonian mechanics questions. I'll be sharing my explanations, and I encourage all teachers, parents, and students to offer any insights or corrections. A 30 kilograms child slides 6.5 m across a horizontal plastic water mat. The plastic surface exerts a 50 N friction force on her, and the work it does is calculated as the product of the distance and this frictional force. As Helena rides down a hill with constant speed, the net force on her is zero. This implies that the frictional force opposing her motion must be equal in magnitude and opposite in direction to the component of the gravitational force pulling her down the slope. This gravitational component is given by milligram sin theta. Aisha is practicing table tennis. She throws the ball vertically upwards, and just as it reaches its highest point and becomes momentarily stationary, she hits it horizontally with her bat. At the instant the bat contacts the ball, the bat exerts a force on the ball, and the ball exerts an equal and opposite reaction force on the bat, in accordance with Newton's third law. Throughout this process, the ball is, of course, also under the influence of Earth's gravitational attraction. Since the force between the bat and ball is significantly greater than the gravitational force during impact, this collision can be treated as a conservation of momentum problem. Therefore, the total initial momentum of the bat-ball system equals its total final momentum. Knowing the masses of both the bat and the ball, along with the initial and final speeds of the bat, and recognizing that the ball's initial speed is zero, as it's momentarily stationary, we can then calculate the final speed of the ball. During the collision, the force from the bat on the ball is far greater than the gravitational force. This large horizontal force causes a substantial change in the ball's horizontal momentum, while the relatively small vertical gravitational force results in only a minimal change in its vertical momentum. For a model of a children's game, students are designing a system where a spring propels a block of mass m along a frictionless track. The block travels up a curved section of the track, reaching a maximum height h where it momentarily comes to rest before returning. Assuming the block is a point mass, the surface is frictionless, and the spring is both massless and ideal, the system's total mechanical energy is conserved. This means that the initial elastic potential energy stored in the spring is entirely transformed into the gravitational potential energy of the block at its highest point. By equating the expressions for elastic potential energy and gravitational potential energy, we can determine the maximum height the mass reaches. If the spring possessed mass, the maximum height the block reaches would be reduced. This is because some of the spring's potential energy would be consumed in accelerating the spring itself, leaving less available to lift the block. Knowing the mass of the block, the students aim to experimentally find the spring constant. Their setup involves systematically changing the compression of the spring. This is their independent variable. They then observe and measure the corresponding height the block achieves, which serves as their dependent variable. After taking their measurements, the students have a table of data. Their teacher advises them to plot height, h, on the y-axis versus the square of the spring's compression on the x-axis. The advantage of plotting the square of x instead of x is that it will yield a linear relationship, allowing them to calculate the spring constant, k, directly from the slope of the resulting straight line. For this task, you'll earn marks for each key step. First, with the provided values for the square of x, plot the height, h, on the y-axis against the square on the x-axis. Crucially, ensure you add error bars to each point for both the x and y values. Your final step is to draw the line of best fit through your plotted points. Here's a breakdown of how the marks are awarded. 4 marks for correctly plotting the data points. 1 mark for correct error bars on both the x and y axes. 1 mark for drawing the correct line of best fit. To find the spring constant, we first calculate the gradient of the plotted line using the rise over run method. When we rearrange the derived equation connecting the height the block reaches with the spring's compression, it becomes clear that the spring constant K is a component of this slope. This allows us to use the line's gradient to determine the value of the spring constant. The Newtonian mechanics section of an assessment is worth 26 marks, 20% of the total 130 marks. This section includes 2 multiple-choice questions, 2 marks, and 2 short-answer questions, 24 marks. Work and energy. A problem about a child sliding on a water mat, focusing on frictional force. Forces and motion. A problem involving a cyclist going downhill at constant speed, determining braking friction. Newton's third law. An example using a table tennis scenario to illustrate forces between a bat and a ball. Conservation of momentum. Calculating the speed of a table tennis ball after being hit. Spring mechanics. Problems involving a spring propelling a block, analyzing height, and determining the spring constant, graphical analysis. Instructions on plotting data with error bars and lines of best fit to find the spring constant. If you need my help, you can add me on WeChat or WhatsApp, or send me an email. Thanks for your attention. Please note Dr. Liu's VCE Physics channel, Dr. Liu's VCE Chemistry channel, and Dr. Liu's VCE Biology channel.